Okay, let's work 6.37. This is getting into quantitation involving heat flows. It asks us what heat, Q, which is the symbol for heat, is needed to warm 22 grams of water from 22 degrees to 100 degrees. Actually, that's a mistake. It's not 22 degrees, it's 25 degrees. From 25 degrees to 100 degrees Celsius. How much heat is required to heat up this 22 grams of water? Okay, so it turns out there's a pretty easy formula to remember for such problems like this when you're talking about heat flows, okay? And if I'm going to kind of write it out in these words, what you got to do is take three numbers and multiply them together. The first one is the specific heat. Second one is the mass. Last one is the temperature change. All these things are important. Okay? Specific heat, mass, and temperature change. I think if you look in the book, if I'm not mistaken, they have a formula C times M times delta T, right? Delta T being the temperature change. Now, each of these factors play a role to compute the total Q. The first one, the specific heat. What is that all about? The specific heat. Well, this number, the specific heat, is the amount of heat energy required to change the temperature of 1 gram of a material 1 degree Celsius or 1 degree Kelvin, because Kelvin and Celsius temperatures are the same, right? They're not numerically the same, but the difference in 1 degree is the same. 1 degree Kelvin is 1 degree Celsius, right? So the specific heat is a number that tells us how much heat is required to heat up 1 gram of some substance 1 degree. It's substance specific. It's intrinsic to the material. Water's got its own specific heat. Steel has its own specific heat. Aluminum's got its own specific heat. And different materials have different values for this. It depends on what the material is, how hard it is to heat up or cool down, how well a conductor of heat it is, okay? So the units for specific heat then are going to be in joules per gram per degree Celsius or Kelvin, okay? Those are our units. How much energy per gram per degree Kelvin. So we're going to multiply that specific heat by the mass, which is going to have gram units, and the temperature change, which is going to have temperature units here, Kelvin or degrees Celsius. So you can see once you do the multiplication, you're left with joules. That's an energy unit. It tells you how much heat energy is required associated with this temperature change. Now, for this particular problem, we want to consider water. It just so happens that water's specific heat is 4.184 joule per gram per degree. That's a constant for water, 4.184 joules per gram per degree. So we're going to plug that number in to this equation. Now, I don't think that number was given in the problem explicitly, but it's kind of a well-known number in this chapter, and it's discussed in the earlier pages. That's the specific heat of water. I'm dealing with 22 grams of water, so that's my mass. I'll plug that in. And then my delta T is my final temperature minus my initial. My final is 100, my initial is 25. So of course that's easy math. That's just 75. I multiply 75 by 22, and by 4.184, my specific heat. That's going to yield me a Q value, which is the heat involved in this particular warming of water. It's 6,903.6 joules of energy. That's what's required if I'm worried about sig figs. I don't have to worry about the temperature too much. I guess you have to kind of worry about that here. I may just round that to 6,900 joules. And that's what's required to heat this 22 gram sample of water up 75 degrees. Please note that this is just to heat the water, the liquid water, from one temperature to the other. The reason why I'm making a point of this is this 100 degrees Celsius. That is what? The boiling point of water. It turns out something interesting happens when a liquid such as water boils. Once it starts to boil, all additional energy that's put into the system is actually used to convert it into a gas, in this case steam, right? Water vapor is steam. So any more additional energy that you put in would actually be used to convert that water to steam, because that conversion from a liquid to a gas is an endothermic process. It requires energy input, okay? So that's pretty interesting. So the temperature would stay, of the liquid water would stay at 100 degrees until that phase transition was complete. All right, but this is just a simple heat flow problem.